So let's try an example talking about efficiency. So I mentioned in the beginning that if I have a normal shock, well, that acts as a diffuser. I have a Mach number that's more than 1 beforehand, and I have a Mach number afterwards that's slowed down. So supersonic beforehand, subsonic, so this is a normal shock diffuser. But obviously, that's pretty terrible. Like it's kind of a horrible diffuser. Why? Because our P02, our total pressure at the end, is way, way less than P01. I've lost a lot there. But we can use that, okay? We can use that to help ourselves and to figure out some really interesting stuff. Okay, so let's think about if we had a normal shock, kind of like, our diffuser that looks like this, okay? Now, we don't have to worry about what's going on here. Just remember that we did our best to design this. And we want to come up with a way of comparing the efficiency here. So this is the actual one. This is the terrible one over here. Actual, and shouldn't put an arrow, it doesn't go there. And this one right here is the terrible one. Well, we can figure out a way of defining an efficiency for this. And now, most cases when I talk about efficiency, it's always less than 1. In this case, this is not like we're just defining a term here. And so for me, the efficiency of a diffuser is going to be equal to, so I'm just going to call it the PR. I'll mention what that is in a second. The pressure ratio actual over the pressure ratio for a normal shock. And when I'm saying pressure ratio, I'm just saying that's equal to P02 over P01. So if I do a good job, I don't do an absolutely horrible job, this should be more than 1. Because otherwise, why am I not just using a normal shock? Like literally, if it's less than 1, you've failed at your job. Okay, now let's come back to this scenario up here. So I've got this actual one, and I know that it has a diffuser efficiency that's equal to 1.5. Okay, so that's great. That tells me something. And let's say that it is working at a Mach number that is equal to 3. So my question would then be, what is my pressure ratio? What is P02 over P01 for the actual situation? Now, this is not actually a hard problem to solve. All we have to do is we first need to figure out what happens for a normal shock, okay? What happens for a normal shock? So we're going to find that. We're going to go to Appendix B. So step 1, we're going to find the normal shock P02 over P01. So from Appendix B, for a Mach number that's equal to 3, what do I find? Well, let's go jump over there and find out. Okay, so I went ahead and jumped over to our appendix. And so if I scroll down here, if I try to scroll down, continue to try to scroll down, it does not like me today. There we go. Now it's moving. I can find a Mach number of 3, which is right here. So I know you can't see the column headings. I wish they travel with us, but this is the column right here. This is the total pressure ratio column. So I see that I have a pressure ratio here, a total pressure ratio of 0.3283. Ooh, it lost 70% of its total pressure, 70% of its ability to do work going across that shock wave. Oh. So not the best at all. So let's go ahead and write that down. See, P02 over P01 is equal to 0.3283. Okay, we got it. Now, step 2, if we're going to solve this problem, is we're going to use our diffuser efficiency to find P02 over P01 actual. So 1.5 is equal to, I'm just going to say pressure ratio actual over 0.3283. And if I then plug that in, what I get then is that my pressure ratio in the actual case, the real case, is equal to 0.492. Is that good? Well, not really. It's still lost over half its total pressure, but we're doing our best to improve that. So we still improved over a regular normal shock, okay? A regular normal shock. Now, the next question you might ask yourself is, like, Dr. Kidd, you've mentioned that you have to have a certain pressure to get these nozzles working at all. Like, I can't just stick it in the wind and hope it's going to work. It won't work. And you're right. So how do we tell what our pressure we need in the reservoir that's actually pumping into this wind tunnel has to be to make it run properly? Well, it's not too hard to figure out. So let's draw it. As a note, I drew it as a perfect one. I'm going to fix that. I'm going to do it the right way. Don't judge me. Okay, so there we go. Perfect. So right here, I've got P02. Right here, I've got P01. And so the question is, what in the world is P01? Because our reservoir is not moving, so the reservoir pressure is simply equal to P01. Okay, well, this isn't too hard. If our flow at the end is moving very, very slow, so my Mach number over here is, much, much less than 1, around about 0. But it doesn't have to be 0. It could just be much, much less than 1. Well, you know what that means? It means that my total pressure, should be equal to my total pressure, and therefore, my total pressure would have to be equal to atmospheric. And so we'll say in that case, 1 atmosphere. If you're not understanding how I'm getting that, just think about it this way. Your static pressure has to be equal to atmospheric at the end. Otherwise, you're going to have something happen. It's either going to lead to an expansion fan if it's more, or a shock wave if it's less. At least in the case where we were going supersonic. We should be moving subsonic here, so I guess that honestly wouldn't matter. But either way, I want my pressure to be equal to what's going on at the end. It has to be because this is subsonic. Like, remember, subsonic things, I can't have pressure gradients. They're going to automatically get rid of them. And so if I know that my total pressure at the end, which is equal to my pressure because it's moving very, very slowly, is 1 atmosphere, then that means I can use this pressure ratio to figure out what my reservoir pressure has to be. So if P02 over P01 is equal to 0.492, and P01 is 1 atmosphere, well, I plug it in there, and so I'll get that P02 is equal to put it the wrong side. That arrow went the wrong place. I really freaked myself out there. P02 is 1. There we go. So 1 over P01 is equal to 0.492. And so my initial reservoir pressure would have to be equal to right around 2 atmospheres, but it's 2.30 atmospheres, just assuming that atmospheric pressure is 1 atmosphere. Okay, so we did it. We figured out for this actual, diffuser, there would be shock waves in here, what our reservoir pressure would have to be to make it actually run. Because remember, you can't just run it with any particular pressure. What pressure you choose will determine if it goes supersonic, we're talking about a nozzle, if it runs at all, or if it ever reaches, that choked flow, which we're looking for in most of these cases. So cool, we did it. Well done.